Okay, welcome back to Feedback Control Systems. This is Module 13.1. We're going to look at design via frequency response. The objective of this module are to look at transient response via gain adjustment. Then we'll look at lag compensation, lead compensation, and then finally lag lead compensation. So we'll start with looking at our transient response via gain adjustment. So we're going to look at finding our gain K here to yield a 9.5% overshoot given a step input in the system. So in our system here, we have a power amplifier, motor, and load, and then going from velocity to position via an integration process as shown there, then having a unity gain feedback system. So we'll just start with a gain 3.6 to start the Bode plot at 0 dB at a frequency of 0.1. So again, just to start our frequency plot here at 0.1, we have a gain of 0 dB just as a starting point, as a reference. And then we can do the phase plot down below as well. So this is based on our original gain here of 3.6, and then later you'll see there's an adjustment being made. But let's hold off on that for right now. So if we want a 9.5% overshoot, that's going to yield a damping ratio of about 0.6 based on our equations shown in previous modules. And what we can do is, given that damping ratio, we can basically calculate our phase margin from this calculation, again, shown in a previous module. We'll see here that the phase margin comes out to be about 59 degrees using that equation. So this phase margin, if I look for that, that will occur at about 14.8 radians per second. So here's 10, 20, so somewhere sort of halfway in between here is about where that frequency is. And again, if I were to go up right here, what you'll see that's about minus 44 dB. So here's 40 and 50. So again, right in the middle of that as shown there. Okay. So what we're going to need based on that phase margin is an additional gain of about 162 before we go unstable, if you will. So, and that's an additional gain. So we already have a gain of 3.6. We add the additional 162. So we now have a gain of about 583.9, which again, multiplied by this 100 in this case, would give us this open loop characteristic as shown here. Okay. Now, if we were to do a simulation of this system, that's going to yield the following table. Based on our specification, we said we want a 9.5% overshoot, which yielded a 59.2 phase margin. And then after we simulated it, what we'll find is overshoot was a little bit higher. We achieved the phase margin. And based on this system, a type 1 system where we start down at minus 20 dB per decade, that would yield our static constant KV. We can calculate that as well. And that's basically what we end up. We could also find our peak time, which is the time at which the overshoot occurs. Again, from our simulation, we could also have worked that through a calculation as well. So given that system, here's the system we have from the previous slide. We now want to build a lag compensator for that system to get the same overshoot here for a step input. But now what we want to do is get a 10x improvement in the steady state error over the previous slide. And again, the previous slide, we had that gain associated with it. So the previous slide had a steady state error based on our type 1 system, a KV of 16.22. So a 10% increase would make KV now 162.2. Okay, and that would result also in an increase of gain by a factor of 10 as well. So notice that K now goes up by a factor of 10 as well. For the open loop transfer characteristic, we can now get our new open loop transfer function and then plot that. And so here, that's what this is in black, called the uncompensated system. Both the magnitude and the phase angle, as you see here, you can trace those in black. That's the uncompensated system that we have G of S. Now, if we want a phase margin of 59.2, well, where did that come from? Well, we knew we wanted a 9.5% overshoot, which led us to a certain damping. That damping then was substituted into our equation to get a phase margin of 59.2. So we know that's the phase margin we want. And what I'm saying here is let's add 10 degrees due to our lag compensator. Based on where that's designed, we also want to account a little bit there. So I'm just saying about 10 degrees for sort of a buffer margin. So we're going to say let's have a total phase margin for design of about 69 degrees. Okay. So this phase margin, if I look at my uncompensated system, 69, so 180 minus 69, so that's about 70. So that's going to be about 110, and that's going to be just right about there. So, oops. Okay, and that's just under about 10 radians per second. So here I'm saying it's about 9.8 radians per second. And then so there at that 9.8 radians per second here, I actually can go up to this plot and see that the lag compensator needs to provide minus 24 dB of attenuation. So again, if I look over here, go over, I'm at about plus 24 dB, so that lag compensator can attenuate or shift that curve down a little bit to get that to 0 dB, okay? But relative to the gain. So what we're going to do is we're going to start by selecting the higher of the break frequency at about 0.98, which is 1 decade below. So we'll go 1 decade below that, and you'll start to see the lag compensator design. So here in blue, the lag compensator design, we're going to go down by a factor of 10, okay? And then the lower break frequency here, so we're going to basically draw a slope of minus 20 dB per decade, as shown there, and then basically get where that intersects 0 dB. We're going to get our lower break frequency at about 0.062 radians per second. And that way we design our lag compensator with 0 DC gain. So that resulting lag compensator, based on that above text, we have our 0 here, our higher break frequency, and then our lower break frequency here, and then this gain here designed so that at S equals 0, this all multiplied divided by this will give me a gain of 1. Okay, so that's our design for our lag compensator. And then once we multiply that together with our G of S, so the GC and the GS get multiplied together, that's what we're going to have for our compensated system forward transfer function. Okay, and that's what you'll see here called the compensated system here, and then lag compensated system here. That's what it'll be in blue. Those waveforms will show you essentially the result. And so we can then do some simulations and compare our specified values with the actual values from our simulation. We'll see again our percent overshoot is pretty much where we want it to be. Phase margin, again, pretty close. Now again, we added 10 degrees of phase margin here to compensate for that. So instead of 59.2, we get about 62. So maybe we could have added 7 or 8 degrees of phase margin. But again, 10 is probably fine. So I think we're good there. And then we get our system pretty much where we need it to be. So I think overall, pretty good for our lag compensator. Now next I want to look at a lead compensator design, but before doing that, I want to give you just a quick background and overview of our lead network and frequency response. So for the lead compensator, we have a given transfer characteristic here, where we're going to have a 0 here based on that inverse time, or basically that location and frequency, and then this one here, note that beta be some value less than 1, and then that associated gain there. So in terms of our uncompensated system that we may have here in black, as we put a lead compensator, unlike the lag that would go down, the lead compensator, we have a lower break frequency here, it then goes up, and then it goes like that, and then the compensated system you can see here fixed in blue. Okay, and so the compensator again starts up here to a finite point, and then maybe comes down here as we look forward in our system. So as I look in, and that's a phase. This was magnitude. I didn't call that out specifically, but that lower one is going to be our phase of the compensator. and then you'll see the compensated phase on the last plot down here below. So you'll see that result here. And what you'll see is, depending on the value of beta that we pick, again, we can sweep beta from, say, 0.1 to here 0.5. You'll see that there is quite a range of impact relative to our compensator design, not only in magnitude but also in phase, right? A beta of about 0.5 only yields about, maybe about a 15 or 20 dB or degree rise, but a smaller beta here has a much bigger rise in terms of that bump relative to the phase. So wanted to provide this as a sort of an initial background here. The compensator phase angle, as we look at this equation and then sort of bring it down to calculate that compensator phase angle, we can write that expression. And if we set that equation, take the derivative of that angle and set it equal to 0 and solve, we can basically look for essentially the maximum value of that angle. So again, this peak or this peak or this peak here, we're trying to find the maximum frequency there. And so what we can do is find that value there as 1 over t times square root of beta. So that's a methodology if you wanted to find where that peak is for this compensator design. So essentially we're looking at that peak here because that's going to help us as we design our system. So if we substitute this information into GC of S, and then we can find essentially the maximum phase shift. So based on our G of C up here, if we take this omega max, substitute that in, a little bit of math later, the key results are shown here in terms of the magnitude and the max phase angle that we would have. So at that frequency, again, what is this max phase angle? And then essentially the magnitude at that beta as well. Okay, so that's the real quick overview of that lead compensators from a theoretical perspective. And for that, I really wanted to show there's this pretty big impact relative to beta and this max point about that as well. So I just wanted to bring that out. So now what we want to do is take our original system here that we've been looking at and now design a lead compensator to yield a 20% overshoot with a KV of 40 and then a peak time of about 0.1 seconds. So a 20% overshoot, again, we can find that relationship to our damping from previous equations, and also what our closed loop bandwidth is going to be from this equation as well, from a previous equation. And then what we can do is relate that to our peak time right there. So if we know our peak time and our damping, we can find our closed loop bandwidth as shown there. So I would say don't just watch the slides, go through. Prove to yourself that you can find that 20% overshoot yields this damping. Don't just take my word relative to the slide. I want you to go back through your notes, through the other modules, and make sure you can make this connection, that 20% overshoot yields that damping. You can find that on your own. And then once I have that damping and the peak time given there, I can literally walk through this. This is not an easy calculation. A lot of errors, possibilities for errors here. So make sure you can physically substitute all this in and get the closed loop bandwidth of 46.6 that I'm showing here. It looks easy. It's on the slide, but please go through the steps. If you don't go through the steps, and if the first time you're going through these steps is on like an exam, I'm just going to warn you now, that's going to be too late to start trying this out. Okay, so please, again, it looks easy. It's nice by plotting it on the slide, but please go through that by yourself. Okay, so given a KV of 40, we can solve for our gain K from that closed loop, from this open loop transfer characteristic here. So I'm taking my forward path gain 100, and then with S equals 0 terms here, I have 136, this 100 down below, and then solve for my K to yield a KV of 40. So again, that's how I would go about finding my value of gain K. That comes out to be about 1440. And then my total open loop transfer function here, once I put that all together, is shown right there. Okay, so that's that 20% overshoot Also, there's a relationship with the phase margin. So here again is that equation. I can get a phase margin of about 48 degrees. Then what I do is I plot my G of S, magnitude phase characteristic, and I'm looking for that phase margin of 48.1. And so again, with that gain, the phase margin is about 34 degrees at omega equals 29.6. So here's 10, 20, 30. Here's 30 in terms of the frequency. And again, if I look at my uncompensated system there, I have, again, a phase margin of about 34 degrees at about that frequency as shown there. So the lead compensator required, basically, if I look at the difference here, where my Bode plot is located, 34 degrees, what my desired is here of 48. Here's my 48. Here's my minus 34. If I want to add 10 degrees of phase margin for my lead compensator, remember when I did my lag, I said I better put in about 10 degrees of phase relative to the lag. So here I got to add in 10 degrees of lead. So when I work this all together, here's my desired, here's my Bode plot, here's my lag, my lead compensator. The lead would need to add an additional 24.1 degrees of phase for that characteristic or that design to occur. So what I can do from these equations that I found for my lead compensator on the previous slide, for the 24.1 phase margin, that would be my maximum phase. That's sort of the peak. I have this expression. I could then solve for beta based on that. And then once I have a beta, what I could do is find my max frequency and also that magnitude based on that beta using, again, the equations that we had showed you for the lead compensator on a slide back. Okay, so I'm walking through my lead compensator design. I know my the amount of phase, and I know sort of that max frequency where that needs to occur. I can also look for break frequencies associated with that, and so that would be sort of the numerator denominator relative to if I set my omega max at 1 over t square root of beta, I can actually now solve for 1 over t and then 1 over beta t, etc. And now I use that information. Here's my 1 over t and then my 1 over beta t here, okay? And then this is my 1 over beta term right there. So I've now designed my lead compensator from that process. And then that final compensated system is, here's my GS from the previous slide and my GC from this slide, kind of multiplied all together. And I have my final compensated transfer function. And what we'll see if I go back one slide, here, just like for the lag compensator, I start in black with my uncompensated system, then I show my lead compensator, and then finally this one right here is my compensated system. So that's that final transfer function that you saw, the G times GC term, and then that plotted. So again, down here for the phase as well, here's my lead compensator. You can kind of see, again, relative to that maximum frequency of about 40 radians per second is about where the peak is. So that's 10, 20, 30, 40. That's about where that peak is, okay, about 40 radians per second. And then again, you'll see that peak up 0 to 45 here. So again, it goes up by about 24.1. So it's always good to kind of go back and forth with your calculations, making sure you're plotting the right thing. And so again, I just wanted to show that final compensated transfer function. And then again, here was our specifications. And then we can actually look, this was when we just did our gain compensated value. And then here's our lead compensated value that we had. And also we had a lag compensated value. You could put that in the table here as well. But in this case, 20% overshoot was the spec. 22.6 was what we had for this compensator design. And when we just looked at just the gain compensated value, again, definitely had a higher overshoot. But again, in terms of the peak time, a pretty good peak time, relative for the lead compensator design. So overall, I think pretty good for that design. Now, we also can do a lag lead compensator, and so that compensator has a lead and a lag part that essentially get multiplied, and so we can see, we can see these values as shown here. And now I'm going to use this term gamma here, separating the higher and lower breakpoints for the lag or the lead compensator. So now what I want to do is let's find a lag lead compensator to yield about a 13% overshoot, given a KV of 12, a peak time of 2 seconds for a unity feedback system with this GS. So now this GS is different from the previous one with that motor amplifier example. So just wanted to make that clear. Okay, so we know our overshoot. So what can we do with the overshoot? Go back, find our damping ratio and our closed loop bandwidth. Again, I'll leave that to you. Please don't just look at the slide and say, yup, okay, I know how to do that. Make sure you can go back and do all of these steps, okay? So I can find that information. And again, here's my bandwidth equation. Previously, the overshoot damping, there was a graph, a curve, also an equation for that as well, okay? So I can solve for my gain K given my KV. So my KV was given. And then based on this, again, relative to setting those equal to 0, I have K over 4 equals KV, as shown right there. And then so again, that's how I got my K term of 48. 48 over 12. 48 over 4 is 12. So I now have my G of S term right there. We can now find our phase margin based on that overshoot from that equation, phase margin of about 55 degrees. So what we're going to do is, based on this plot here, G of S, that's our uncompensated system here in black, both for the magnitude and phase. And so what we're going to do is we're going to say, okay, let's select just under 2 radians per second as the new phase margin frequency. Okay, so just under 2, okay, just under about 2 there is our new phase margin frequency. So the uncompensated phase at that frequency is pretty much 180. It's about 176 degrees. So we might want to add about minus 5 degrees for a lag compensator. The lead compensator would be in then turn about 56 degrees. Why? Because I want to desire to 55. If I pick this frequency here, the uncompensated system's at minus 76. If I add minus 5, and then I want to be here, so I basically need to add 56 degrees for the lead compensator to get my overall net at about 55 degrees. So the lag compensator does not impact the K term. For KV equals 12, so that system, nor the phase margin provided by the lead. So what we're going to do is we're going to try to pick a higher break point about 1 decade below the 1.8 radians per second. Again, that's where we had picked that phase margin of 55 degrees from the previous slide. So we're going to go about 1 decade below. So what that's going to do is we're going to define gamma as 1 over beta, and essentially that will come out to be about 10.6. So again, given our beta term here of 0.094, so inverse of that's about 10.6 to get our 56 degrees phase margin from the lead, as we stated on the previous slide. Okay, so the resulting lag compensator is going to be shown below. So we know our gamma term right here. And then we know our lower break frequency, okay, and our lower break frequency here about 1 decade below, and we see that other point right there of about 0.183. Okay, so we can design our lag compensator as shown right there. And then the lag compensator system open loop transfer function is going to be this. So again, that takes our lag compensator along with our G of S from the previous slide. And again, part of the 4.53 is due to this term, and then the other term from the GS from the previous slide. Okay. Now we can design our lead compensator. We've already have our gamma from up above, and so we can design our lead compensator here based on our 1 over t and gamma over t as shown here. So 1 over t would yield about a factor of 0.56. And what we'll see is when we relate for our lead compensator, our maximum omega, based on that t that we had found, is we get a max of about 1.8 radians per second. That's again what we desired, right? That's what we picked here, that 1.8 radians per second. And then so we can basically have the beta term. And again, there's our beta term. So again, we have all these systems in place as part of our design in terms of finding our t terms as shown right there. So the final, we have our lag, we have our lead, we have our G of S, kind of putting all those together here. Our full lag lead compensated system is shown there. And then we could do our simulations here to predict based on our overshoot. Overshoot is actually a little better than we had picked, similarly with our peak time. And if we look at our closed loop bandwidth, a little bit higher, about 2.3 to about 3. Okay, phase margin we had set about 55, or a little bit better, 59.3. So overall, I said relative to this system, it looks pretty good. Okay, so that's pretty much going to be the end of this module. And again, what we did with this module is showed you from a lag, a lead, or a lag lead system, different ways in the frequency domain to come up based on desired overshoots. That leads to damping, that leads to phase margin, that leads to an approach using our Bode plots to design any of those three systems that we talked about. And we tried to show you sort of a step-by-step methodology and how to go about this. Again, including a little bit of phase either due to the lag or the lead, maybe 5 degrees, 10 degrees, whatever. You'll get some feel of how to estimate those as you go forward. Okay, so that will conclude this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.